Okay. Flying around. Oh, sure. Okay, sorry this late afternoon lecture. Also, today's lecture was supposed to be the Wednesday lecture for the morning, and there was supposed to be no problem session, and there still is no problem session. So I chose a kind of a side topic. I mean, it's the same stuff, but it's like what happens over complete intersection rings, which was like the example we saw was one. But so I want to talk about those for today. But it is a side topic. You don't need to know. It might help you understand the stuff we've been doing better, but you don't need to like know this for understanding the next day. Okay? All right. Okay. So what we're going to do in this lecture is we are going to build 3 resolutions. And they're not necessarily GG algebra. Okay, so 3 resolutions over. Okay, now I'm going to let you catch up. So this is a side lecture. What I mean is it's not necessary to understand Thursday and Friday, but it might help you get more familiar with similar things. Okay. So this pair of words, complete intersections, we all get very lazy, and we write it as CI. Some people put capital CI, capital I just do CI, okay? So from now on, CI means complete intersection. I have to define it for you. I haven't defined it, but anyway. So we are going to build 3 resolutions. They're not necessarily DG algebras over CI rings. Okay? So why am I doing this topic if they're not DG algebras? What we're going to do is using some DG module structures that are lying around. Now that's a little bit of a lie because they won't be, at first they'll be DG module structures and then they won't be anymore, but and they're lying around for complete intersection rings only. Okay, well, mostly. Okay, so what's a complete intersection ring? So by a CI ring, we will mean, but also if you have any question, you can't read something or didn't hear something, just say. But you have to shout, I can't hear you. Okay, so by a CI ring, I'm going to mean a local, a ring of the form R equals Q mod F1 up to FC with, now, so I can make a decision here. So let's just say with Q, and let's call the maximal ideal N local. So this is the maximal ideal. So it has one maximal ideal and it's N. And I think I'm going to assume it's a regular ring most of the time. It doesn't always have to be for the things I'm saying, but then I have to sometimes say something else. So I mean, actually, it's sort of mostly not today, but I might forget sometimes to say it when I need it. So I think maybe we're just not going to assume it, but okay. Anyway, but mainly F1, so N, F1 up to FC are in the maximal ideal, and they are a Q regular sequence, which part of the definition is that they're in the maximal ideal. Okay? Does anyone not know what those words mean? I'll just say it quickly if you don't. Okay, so I'll say it out loud then. F1 is a non-zero divisor on Q. F1 is a non-zero divisor on Q. F2 is a non-zero divisor on Q mod F1, etc. Right? Etc. Not obvious. Keep modding out by everything up to that point, and the next one should be the non-zero divisor. Okay, so these rings are very nice.
It doesn't have to be a maximal.
It does not have to be a maximal regular sequence. No. It could just be one thing, even. It does not have to be a maximal regular sequence. Okay? Yeah, so in fact, if C is 1, if I just have one equation, it's called a hypersurface. And now this is the one point in the entire week where everybody in the room who's a geometer and an algebraist is happy. Right? Okay. Anyway. Okay, so actually, to really define a coplanar section, you're supposed to say any ring, any local ring whose completion looks like this. And if it's not local, you're supposed to say localizations look, complete. Okay? So, but I'm just going to do this because this is lecture, right? So we don't do the most general case. And all the other things follow through for everything else mostly pretty easily, so we'll just stick with this. Okay, so I'm going to sort of start with two resolutions. The second one is going to have two versions, but whatever. Okay, so that's most of today is two resolutions, and then I'm going to say a little bit of applications at the end. And so that's the plan. All right, so the first one is actually something you've seen already today, and we did exercises on, but I want to tell you the theorem. Okay, so these are called embedded CI. Okay, so for certain special quotients of a CI ring R. So you did this, you joined variables during the entire exercise period, right? Okay. The process of adjoining variables, the process of building, so let me be more precise, the one where you use divided powers, just so that I include characteristic things to work in characteristic P. So of building, let's say an acyclic closure, so that uses exterior and divided. Powers stops. So it stops at degree 2 variables. And that's what we saw in the example that we did together, which is wonderful, right? And then you did an example that was horrible. You had to go on and find some degree 3 variables, and it was really hard, right? Okay. So let me tell you this theorem. When is it that it stops like that? And then as the week goes on, we'll discuss this kind of stuff more. Okay, so here's the setup. Oh, and this is all, well, I'll write that later. Okay, fine. So first we're going to let R be what I said over there. Okay, I'll write it again. R is Q mod F1 up to Fc, and this is a regular sequence on Q. And I don't really need Q regular here, so Q can be anything. Local is good. Ooh, I didn't charge my phone. Uh-oh. Okay, so now take another regular sequence. Take another Q regular sequence. sequence, A1 up to AM, let's say. So this is another complete intersection ideal when that's generated by these. So such that, let's call it something. So I'm going to call it I tilde. So that's the ideal A1 up to AM. Contains the ideal up there, F1 up to FC. So it's a bigger ideal, which means you can write the quotient. But first, let I denote the image in R. So I was just like I tilde R, the image in the quotient. Okay. This is an ideal in Q. So this line of the board is happening in Q. Okay. So let that denote that ideal. So essentially we have Q mapping onto the smaller ideal Q mod F1 through FC, and then you mod out by more stuff Q mod A1 through AM, which is I'm calling I tilde, but really that's like, see, these A's contain the F's, so I've modded out by the F's also, so you could think of this as R mod I, which is also generated by the A's, okay? Okay, so this is the case in which I can resolve in 2 steps. Any questions so far? That's the map we're going to look at. So the main point is, if this ideal were a regular sequence in R, it would be really stupid to resolve it. A regular sequence over R you can resolve using the Kazoo complex, and that's it. But it's only a regular sequence over Q. Once you go to R, mod the F's, this is not a regular sequence over this quotient ring. So that it's going to require more than the Kazoo complex. We're going to resolve over R. Okay, so this is called, I is called I, or R mod I, is called an embedded CI, embedded complete intersection, ideal, or R mod I is called an embedded complete intersection ring. Okay, and so the theorem of Tate, I need a little more setup. I think I'm gonna go ahead with a little more setup before I write the theorem. So, because the F's are contained in this ideal that you modded out by, each F can be written as a combination of the A's. So let's. Yes.
There's nothing more special about these A's. Can't they just be the F's?
Q regular sequence in the maximal ideal.
Yeah, can't they just be the F's?
They can be the F's.
Oh.
And then the resolution I'm going to write down is too big. It's not minimal. It would be easier to just resolve it by just saying R, but yes, there's no, but if, so I'll get to your question. Actually, I think I put it as an exercise. If the A's are not the F's, if the F's are contained, which way? If the F's are contained in the maximal ideal kind of A's, then the resolution is minimal. So, but if not, it's like you do a bit of pointless work. Okay. So more setup is, let's write each Fj as, so you write Fj is some combination of the A's. So I decided to call them Rij. Oh. Okay. So, can we make the A's G's? Or I'm going to have to change everything. Okay, so these are all G's. I'm so sorry. Every A, all the A's are G's. It's not that hard, it just goes like that. Okay. Sorry. Okay. So let's write Fj as a combination of the Gi's. And so these are some kind of coefficients in the ring Q. Okay. All right, so now I'm going to tell you something that you've pretty much done in exercises, but this is the theorem. So the theorem of Tate is in the same paper where he introduced these Tate resolutions, which he didn't call Tate resolutions. So with the notation above, the semi-free gamma extension A, so I'm going to call it A just for convenience. So take R. So the first thing we usually do is try to degree 1 generators to kill, the degree 1 variables to kill these generators, G1 through Gm. So let's adjoin E1 through Em. And then you need to adjoin some degree 2 things. If you were over the polynomial ring, the Kazoo complex would be exact. But it's not because of these stupid equations that we modeled out by. And do you remember where the degree 2 variables came from? I heard someone muttering something, but I couldn't hear what it was. Do you remember how we got degree 2 variables?
Yeah, replace one of the variables of the equations with one of the.
Yes. So you take each of these f's, which is a polynomial in the variables, and replace one variable in each product with an EI. Okay? So each of these will produce one. So yes, except now it's not variables, it's the G's, because you were resolving the residue field, which was where the G's were all the variables. You were modding out by all the variables. But now we're modding out by G's. So instead you pull out a G. So you write F as something times G, and now instead of G, you put EI. Okay, wait, so maybe here I should have written the boundary of EI is GI. So then I'm going to take this, and F is 0, so then if you take the GI and replace it with EI, it's a cycle. Okay, so I'm going to take T1 through TC, because that's how many F's I have. And I want the boundary of TJ to be the cycle, the sum of R, I, J, E, I. So I've just taken the G and made it an E. So notice if you do boundary to this, the E becomes a G, and you get Rij, Gi, which is F, which is 0 in the quotient ring. Okay, so this goes to 0. I mean, this goes to F, J, which is 0 in R. Okay. All right, so this is step 2, and the theorem says that's it. So I'm done. So there are no, it's exact now. So this is already a resolution. You need no more variables. I'll finish the sentence somehow. This resolves R mod I as an R algebra.
Question.
Yes.
What about the converse?
Oh, good question. If you can stop at degree 2 variables, is it always an embedded complete intersection? And the answer is no. So there's one more thing it can be, but it turns out there are more things it can be. Okay, so there's one more thing it can be that people figured out, which is, I think it's these exact pairs of non-zero divisors that I don't know much about. And then there was a question of whether, if it stops at degree 2, is it either this or the exact pairs of non-zero divisors? And I think the answer to that is no. There are even other things it could be. Okay. Exception, big exception, we're going to learn later this week, is what you're resolving here is the special module, the residue field, then the answer is yes. That's the only thing it could be is complete intersection. Oh, but I'm also starting with a complete intersection, so that didn't really help. And the residue field is already, okay, sorry. So I'm talking about sort of a more general theorem that we'll see later in the week, is if you don't even know that it's a complete intersection and you start resolving and it stops, then you do know something. Okay, so that was Tate's theorem. Okay, and so I guess I'll just I'm not going to do any examples, but our running example is exactly like this. Our running example was resolving K adjoin xy mod x cubed plus y cubed onto K, which is really it's really K of xy mod x and y. Okay? So there's one single F equation, F1, and there are two G1 and G2. On the ring Q, this is Q. They're both regular sequences. This is a bigger ideal that you've modded out by, and so Tate's thing works, and that's why we were able to stop in degree 2. Yes?
In the original example, it was the formal power sequence.
Yeah, this is my problem. I always forget to make it local, so let's go like that. Sorry. I have a problem, like for decades.
And to the other.
On the right?
Yeah, it doesn't matter because once you mod out by x and y, it could be either, but yeah, you're right. I sort of should put that. Thanks. Yeah, so that it's the same Q. Okay. And sort of anything like that. So you could try one by yourself sometime. I mean, any complete intersection, mod another complete intersection, and you'll get this. Okay. So for example, whenever you have the residue field, so whenever you have R is a complete intersection, so it looks like Q mod F1 through FC, and that's a regular sequence. And then you're going, and Q is here, Q here has to be regular, a regular local ring. And then you go to the residue field, which is Q mod its maximal ideal N, but that is also generated by a Q regular sequence because it's a regular ring. So the maximal ideal is generated by a regular sequence. So the residue field over a complete intersection will always satisfy this property and is beautiful, always beautiful to resolve. Okay, so I think that's all I wanted to say about that. Any questions? Okay, so now I want to tell you about another famous. Okay, so the problem is this is kind of restrictive. I mean, when is your module going to look like another regular sequence? It isn't usually. So what else can you do?
Resolution be minimal or
Yeah, oh, well, that's an exercise in your exercise. Oh, you're not doing these exercises, right? So they emailed you some exercises. One of them is that if the F's, so the F's, Fj's, are actually contained in the maximal ideal times the, oh, no, wait, sorry. Yep, times the G's. Then this is actually minimal resolution. So not just minimal in the sense of you've made minimal choices, but it's actually a minimal resolution. The boundary of the complex lands in the maximal ideal times the complex. Okay. And you can probably see why, but okay. Okay, so that was the first first kind of resolution, and now I'm going to talk about more general resolutions because most things don't look like this. So more general resolutions over CI rings. Because that was a very special module going on in another regular sequence. Okay, so let me tell you the strategy. You want an R-free resolution of some R module M. And all of today, R, which I've erased, R is a complete intersection. Okay. Okay, and so what you can often do is start with a Q-free resolution of M. Is that better? If Q is regular, local, why is it better? It's finite. So e.g., well, I guess I'm not really assuming that. Yeah. So if Q is a regular ring, regular local, then this thing is finite. I mean, even if it's just regular, Noetherian, whatever. Okay, it's a finite resolution. So it's short, and you can usually compute it. And if Q is like a polynomial ring or a power series ring, you can use Macaulay and compute it and finish. Okay, so this one is usually doable. Okay, and this one looks crazy, right? Probably, if you start computing. All right, so the question is, so notice the following. You want to go from this over Q to get to R. So a little bit, the question is, how are Q and R related? So note that the Q-free resolution of R is, well, so it's just, you got them on a regular sequence, so it's the Kazoo complex. K adjoining F1, K of F1, FC on the ring R. I mean, nowadays we're also writing this as R adjoin E1 to EC, such as the boundary of EI is FI. I guess we have two ways to write the Kazoo complex. Q, thank you. Great, these are all 0 in R. Q. Okay. So the question is, and this is this DG algebra. Does that help us? So the question is, does this structure, namely that it's a DG algebra, does it play a role in building an R-free resolution of M from the other one? So from the Q-free one. Okay. Well, sort of. It's off some. So, in many cases it does, and in many cases it doesn't. But then you could do something kind of close to that. So that's the two things I want to talk about for the second part. All right. So what do you do? 5% battery. Okay. So this history goes back to Shamish. So it goes back to Shamish in 69. That's for hypersurfaces. But when you go mod more equations, it goes back to Gullikson and then Eisenbud. mean, this was in 62 and this was in 80, but not all of the thing was written out explicitly as a resolution here, but a lot of the structure was already developed here. It's kind of a combined thing. Oh, sorry, that was not 62, that was 74. Oops. For in general, for CIs. Okay, and Eisenman also discovered the beautiful role in doing this. He also discovered the beautiful role of matrix factorizations. Whenever it's bounded, so whenever the resolution has bounded ranks. And I'm still over a complete intersection ring, otherwise that's not the case. And it also culminated in Avrama's definition of support varieties in 89, which has become a very important development in the field too, that I'll talk about at the very end of the talk. Okay, so I'm going to kind of discuss the next result, these results. I'm going to give them the easier case first. Okay, so here's the setup. Okay, we still have the same complete intersection ring in the resolution, so we have R is Q mod F1 through FC. This is a regular sequence in the maximal ideal, etc., etc. So I'll just say this is a Q sequence in N, and Q is local. I don't really need Q regular here. I'll just say Q local. Okay, so start with sorry, M is an R module. Sorry, I forgot to say that. M is an R module. To start with a Q-free resolution of M. Okay, so it's F0 goes to M, F1, and so on. And it actually can be infinite, I think. And okay, so but it could be finite if you have a regular ring, which is awesome. It doesn't need to be minimal. It doesn't need to have a nice structure. It doesn't need anything. Okay, not necessarily a DG algebra or anything or minimal or anything. I don't care. Just free modules. Okay, so since each Fi annihilates the R module M, because M is an R module, and R is Q mod F's, so the F's kill M. It means that multiplication by Fi on the complex F is null homotopic. So that means it's homotopic Fi, multiplication by Fi is homotopic to the zero map. What that means is i.e., there exists a map S, a degree, so map S from all the Fn's to Fn plus 1s. So this S, let's call it Sn for all n. So it's a map from F to F, increasing degree, with Fi equal to S, whichever S, composed with the differential plus the differential composed with S. And by Fi, I mean multiplication by Fi on F, on the complex F. And these are also maps on F. on F. Right, the differential takes Fn to Fn minus 1, and the homotopy takes it up plus 1 again. So you end up in the same degree. Okay, so you have all these homotopy maps. And so here goes the, is this okay? So why is this true? This is by something called the comparison lemma, comparison theorem. If you look in a homological algebra book, you'll see it. Okay, so let's look at these homotopies. So special case is the first resolution I'll talk about. The special case is if, so it's kind of cool. These homotopies go in degree up 1. There's some kind of a map that goes up 1. Do you feel like the map is like multiplying by an imaginary degree 1 element going up? Okay, but this didn't have any kind of a structure of DG module over anything. But it feels like you're multiplying by an exterior variable of degree 1, and it's moving up. It feels like this is a DG module over the exterior algebra, over the Gazoo complex. Okay, well, if these maps act like the following, so if Si squared is the 0 map, and Si, Sj is the same as the map minus Sj, Si, minus, that means they are acting like an exterior variable would act. If you multiply something, if this had a DG algebra structure over the Gazoo complex, and you multiply by EI, and it's doing the map Si, and then you multiply again, and it's doing the map again, you're multiplying by EI squared. But that's 0 in the Gazoo complex, right? So it's sort of saying you have a well-defined, so then F is a DG module over K equals K, the Gazoo complex, K F1, Fc on Q. So the DG module on that, where, again, this is like Q adjoin E1, EC, and the differential of EI is Fi. Okay? And so via, you just define EI times anything in F, so any X in F, you define it to be, just do the homotopy Si. So the Si homotopy, it moves up in degree 1, and it seems to have the right properties to square 0. So you could just define the structure over this lovely algebra. And the anti-commute, the homotopy is anti-commute, so that means the action of EI is anti-commutes, which it needs to for this. So this is really a free algebra modulo that the squares are 0 and it anti-commutes. So you can define a free algebra on anything just given some maps, but since the relations in the exterior algebra are hold for this definition, it is a module over that. And conversely as well. So the converse is also true. And conversely, yeah, also. It's the same idea. If you have a DG module structure on this resolution over this lovely DG algebra, then multiplying by EI takes you up in 1 degree. Just define Si of anything to be EI times that anything for X and X, for X and F. And these will be null homotopies, or FIs. So it's reversible. Okay. All right, so you always have these homotopies but if they happen to satisfy these properties, this actually has a DG module structure, which is enough. What are we trying to do? We have a Q resolution. We're trying to get to an R resolution. So we're going to do that now. Okay, so the theorem is, and this is from Gullikson and Eisenbud. Sorry, and Shamash also. Okay. Is that it is with the notation up above. So with the notation and information. So with the setup above, we can make a resolution. So an R-free resolution of M is given by, and it's going to look, I'm going to write it kind of all compacted instead of writing it as a complex. Okay? So it's going to be, I'm going to call it G so I can just talk about it. So it's going to be something, D tensor F. I have to tell you what all these things are. So F is the resolution over Q. Okay, D, I have to tell you what it is. And these are all Q modules. So this is over Q, I guess. You need to bring them down to R. So you tensor down to R. So I guess I could write that as D bar tensor over R with F bar if you want. You could tensor both of them down. They're free modules, you just bring them down to R. Okay, where? Okay, so first, S, which didn't even show up here, but let me tell you what S is a polynomial ring. I'm going to write it Q adjoin T1 to TC. And then D is, so it's the graded HOM over Q from S into Q. So it's the dual of S. Okay, this is actually the divided powers. It doesn't look like it. Divided power, just module or something. It's not as an algebra. Okay, let me explain. So if you have a vector space and you dualize it, you get a basis for the vector space gives you a dual basis for the dual vector space. Okay? So now the basis for D. So before I explain the complex, I have to, I've given you the complex kind of, but I have to give you the differential and I have to explain this a bit more. I need to first just explain D. So D is, so a basis for D is really the dual, so it is the dual to a basis for S, because it's a dual, right? It's an infinite free module over Q. The polynomial ring is an infinite free module. So if you dualize, you would get, this is infinite direct sum. If you dualize, you will get an infinite product, but we do a graded dual, and that way it's still a direct sum. So it's, okay, so anyway, the dual, so what's a basis for the polynomial ring? So here, that's just monomials, right? Monomials in the TIs, in the variables T1 through TC. So the dual basis is written as monomials like x1 to the n1 up to xc to the nc. The same way we write divided powers. And then the n okay, sorry, this and, so wait, you also need the 1, the empty monomial 1. So 1 and these guys with ni bigger than or equal to 1. No, that's not true. With not all ni equal to 0. Not all ni equal to 0. Why don't I just forget the 1 and just leave it like this? Okay, ni bigger than or equal to 0. I need to read my notes instead of just talking. Oh, whatever. And also, what am I running x's for? They're t's. The variables are called t's. Okay, so and if you have the basis for the dual vector space, the original, this is the hom. S acts on this through the first component of the hom. Okay, and as such, what does it do to this basis? Huh?
I mean, isn't it kind of odd to call those the variables?
Yeah. What? Oh, couldn't hear you.
This
Sorry.
is the dual basis, right? So
This is the dual basis.
Probably makes sense to call them.
You're calling the dual also T.
Oh, okay, sure. I'm going to call them T stars. Okay, or some people just call them a different letter. I'll put stars, it's okay. Okay, thank you, good point. All right, and then how is it in S module? So with the S action, it's via the usual action on the hom, so as usual. But what is it in terms of the basis? So anything in the polynomial ring is a combination of monomials. So T1 to the, A1 up to TC to the AC. And how is it going to act on one of these? T1 star parenthesis B1 up to TC star parenthesis BC. Okay? So the way it acts is it just removes. It removes variables. I'll explain that in a second. So you get T1 star to the B1 minus A1, and so on. TC star to the BC minus AC. If all the BI's are at least as big as the AI, so that when you subtract, you get at least 0. Yes?
Over there, when you write special case, and then SI squared is equal to 0, what do you mean by that? How do you compose SI with itself?
So each Fi gives me a homotopy, Si, that's a map on the entire complex F that I don't have on the board anymore. So it doesn't mean in the ith position, it's corresponding to Fi.
Oh.
Fi gives you a homotopy on the whole complex F in all degrees. And to compose it, you just do it twice. And I did not put a subscript for what position I'm in at all. So this subscript is supposed to correspond to the F. Each F gives you a whole homotopy, which is a whole map on the entire complex to itself of degree 1. Yeah?
So the N is the S on
Yeah,
the
so
index?
this is wrong what I wrote. Thank you. So what I wrote here is wrong. This should just be dot.
Okay.
Yeah, so, this should be I. So what I meant to say is Si in degree n goes from n to n plus 1. Sorry, that should have been S sub I in degree n. But S sub I exists in all degrees. Thank you. So this should be Si in degree n. So each F gives you a homotopy that's a map on all of F to all of F in degree 1 higher. Okay. And then this is 0 if else. Okay, so what does this even mean? Like, what? So let me just explain that really quickly. Okay, I was going to say at some point I'm going to lose power, which happened. So this is almost time for a break. Let me try to finish this. Okay. Notice that if you multiply on the polynomial ring by ti, it goes up in degree, right? So this on the home, it reverses the arrow. It undoes the map, which erases the ti. Okay, so the action of s on this thing is it erases ti's. So if you have all these t's acting on these, it just keeps, so this erases a1 copies of t1 from here, so you get b1 minus a1. It's just acting on the dual. Okay, so that's what D is. It's a Q module. It has an S module structure, which we're about to use in the differential. And this is the original resolution F. Tensor them together. And tensor it with R. Oh, that's so nice. I was going to give you a break, but that's okay. I'll give you a break also. But the differential, now I'm going to mess it up, on something in here is going to be, maybe I'll just write it as A tensor B. I don't have my notes, so this is going to come out really badly. So what's going to happen is you're going to keep acting by each of the variables on this, and at the same time act by the homotopy on this. So it will erase the variable here, and it will do the homotopy here. So this will go down in degree, and this will go up in degree. Oh, but I didn't tell you that these have degree 2. Okay, so let me do that. Okay. So it will be a sum over all the variables, 1 to c. You do, which one's A? A's and D. You multiply ti by A, and then you do the i's homotopy to B. And what I forgot to tell you is that where in that complex, the degree of each ti should be 2. So if I erase the t from here, it goes down in 2 degrees. And I do a homotopy, it goes up in 1 degree. So altogether, I've just gone down 1 degree. So the differential went down 1. Did I forget something in the differential?
The TI's have degree -2. Then you're missing the difference.
Okay, sorry. Ti star has degree. Sorry, I call them all Ti usually. So they have degree -2. Thank you. -2. -2. So then the degree of Ti star is 2. So if you remove 1, it went down 2.
I think that's still reversed.
Because you remove a Ti when you do this. By removing a Ti, you remove the degree 2, so it went down. And the homotopy goes up 1, so it goes down by 1. Thanks.
One more thing. On the differential, you still need the differential back.
Yeah, so what? Yeah, what happened to, that's what I was wondering too. What happened to the differential of that? Oh, it's plus. Right, okay. Plus, it's in the second one tensor differential of that. Thank you. Yeah.
Applies to A tensor B.
Oh, that's true. I forgot to do A tensor B. Woo! A tensor differential of B. Good. Just going? Yes. Thank you. Okay, now we take a break for 2 minutes while my iPad charges. Thank you for starting to charge it. Okay. So I'll tell you for a second about the proof. So this is. Oh, did I ever say the words that this is a resolution at the end of it? Well, you didn't know. Well, there we go. Is an R resolution of M. R free. resolution of that. Okay, I'll just tell you one tiny bit, which is the key to why this is true. It's in Tate's paper. It's a very nice little thing, and it answers a question you might have had, so I just want to say it. Okay, if you have a DG algebra A, and then you want to start killing a cycle, and Z is a cycle, and you want to kill it, and then you form A of X such that the boundary of X is Z. So this is our construction to kill this cycle. The thing that is worrisome is that it kills the cycle in some degree, n. But now you added more stuff, and it might have caused more problems later, right? More cycles than you had before, which is okay, because you can kill them later. But in Tate's theorem, you want to stop at degree 2, okay? And part of the key of why you can stop is that, part of it is something else, but part of it is also that there's not a lot of extra cycles not a lot of extra homology being created. In fact, none. Is that doing this that killed this did not cause other problems. So let me write that down. But you need a hypothesis. So if the element Z is what's called a graded non-zero divisor on the homology of A. That's the entire direct sum of all the homologies of A. That's again in algebra. What does graded non-zero divisor mean? It means if it's it means a non-zero divisor if it's even degree, and it's allowed to kill itself if it's odd degree, because in odd degree everything squares to 0. So essentially it says that if Z alpha is 0, that implies that alpha was already a multiple of Z, and this is if Z has odd degree. So in odd degree, it's allowed to kill Z. Z is allowed to kill Z in any multiple of Z, but nothing else. So if that holds, then you did not create any bad homology. So then, in fact, that's if and only if. I always forget that. The homology of this new thing you built, A of X, is actually just the old homology mod what you were trying to kill. Yeah, it's the old homology of A mod Z times the old homology. So you killed what you wanted to, and you made it smaller. You did not create new homology. So no new homology created. Now, of course, you need this condition, but over a CI, that's kind of the key. The exterior algebra for embedded CI, the exterior algebra. Whoa, this was the proof? Oh, I think I'm falling asleep. This is the proof of the first thing result from today. Of the embedded CI result. Embedded CI result. I'm sorry. Whoopsies. I meant to say this earlier. I actually meant to say this last time to prepare for this time, but it ran out of time. Sorry, so this was for the first result today. The proof of this is different. I've seen various proofs of this. Okay. Oh boy. So, if you have nice homotopies which square to 0 and anti-commute, then you have a Kazoo module structure, and you can just write the resolution down. If not, so the general case is if you don't have Si squared 0 and Si Sj equals minus Sj Si. That's a minus sign, minus. So if they don't square to 0 and anti-commute, you don't have a Kazoo, but don't have a DG module structure of the Kazoo complex. Okay, that seems bad. These are not 0, but they're actually 0 up to homotopy. So they're almost 0. So then it turns out, oh wait, I have to switch lectures. Hold on. Lecture 3 notes. They still vanish up to homotopy. So you create homotopies, you define a bunch of homotopies that tell you that. And then those homotopies might not be that nice, but they're kind of nice up to homotopy. So you define more homotopies that describe how far those are from being nice. And this goes forever, and you build this whole structure of what's called a system of higher homotopies. So I think I'm going to define it. I can't decide if I should do it. So you should just read it someday. What do you think in the back? Should I define a system of higher homotopies? Not? Yeah, I think not too. Huh? It's what I said. So they still vanish up to homotopy. Define these. But then they're not perfect for some reason, some combination of these, some combo of these. You want equal to 0, but that might only be true up to homotopy, but that's only true up to homotopy. So you write these, and then you continue going. So this is called a system of higher homotopies. And you can still build a resolution, it just has more maps in it. Okay? So I'm going to call these homotopies something. Yes?
When you talk about the D is related to non-zero divisor.
Yeah.
That thing there is a if only if or because there is a
Yeah, this is the definition. Sorry. Sorry. Oh!
But like there is a if and if only if I don't know.
Yeah, so, sorry. Oh, sorry. I think the circle thing is equivalent. Yeah, what did I mean?
What is
Can
homology?
you circle the other part?
Is the homology C? Is equivalent to what? The D is equivalent.
So
Okay.
what is
So
the
not
term?
if only, okay. If if only is not only.
If it's a gradient non-zero divisor? Yeah, no.
Then this is true.
Then no, no.
Okay.
I think so. Okay.
And what's telling us that these homotopies are going to vanish after homotopy?
Yeah, that's a good question. I don't remember.
Or maybe just the
Should the square?
Maybe just in the first step, like if
Yeah, I know. Like, why is this homotopic to 0 when it's not 0?
Is it still because the FI is
Kill M? Is it going to be like there are two lifts that would both work, 0 and SI squared would both be lifts for something? So what?
I think you could just show that the SI squared is cycling on right? And then since the free resolution basically, I mean, it's like an inductive argument, right? It's inductive. So it's not
It's inductive, but I don't remember the first inductive step. Why should SI squared? Homotopy to 0. Oh, no.
The home complex.
The home complex?
Is like a degree 2 now. So like when you take it's something about.
So hom F to F, in that hom FF complex, SI squared is a degree 2 map.
And so that says that SI squared is an x negative 2.
Oh.
No homology in x negative 2. And then you could cook it. It's a little technical.
Oh. Ah, okay. So being homotopy to 0 is the same as if you look at SI squared as an element of Hom FF, which is a complex that you looked on in the first problem set. It's the same as saying in that complex, it's a boundary. But that complex it's got no homology.
Not in degree 2, in degree 2, that corresponds to x.
Oh, next -2. Okay. So, right. So exactly the degree we want, because the homotopies go up in degree. So exactly the place where we want, Hom FF, the homology of it is x minus 2. I mean, it would not minus 2, which is 0. There's no x minus 2. And so the SI squared is in there. Well, wouldn't an SI be in x minus 1? It's not homotopy. Okay. Okay. I'll say more next time after we talk. Huh?
It's not going to be a cycle.
Oh, it's not a cycle. Okay, this one's a cycle.
Exactly.
Okay, so this is a cycle in the Hom FF. Okay, but the x is x minus 2 is 0, so in fact it's also got to be a boundary in there, but a boundary in the Hom FF complex turns out to be something that's null homotopic. In fact, the thing that it's a boundary of is the homotopy for it. So you can read this in Eisenberg's paper or in Avramov's infinite free resolutions. Okay, so if you do this, you can still put together the same complex G, so it still looks like D tensor F, and then tensor down to R. You're done, so make it free R modules, but the differential is worse. So the differential still has the 1 tensor of the differential of F, and it still has like these homotopies, the first set of homotopies, so the SIs, so you multiply by T, I. In this degree, I'm not even putting A tensor B. I'm not applying it to an element, I'm just writing the math. So it's multiplication by Ti and applying the math Si, I equals 1 to C through all the F's, all the equations, plus higher homotopies. So essentially you do a sum over sort of all monomials in the Ti's, in the T's. Tensor, for every monomial, there is a kind of a corresponding higher homotopy. Some kind of an S. I'm not writing any subscripts or superscripts. So like, for example, for Ti squared, there's the homotopy for the Si squared being homotopic to 0. So you do all these monomials, and at the same time, the higher homotopies, you made it, and that huger differential. So it's kind of the same size thing, but it has a lot more going on inside of it. Okay? Okay, but because it's the same size, we get some corollaries from this. Okay, so let me see how much time I have. Okay, good. So I want to do applications very, very quickly. So the only reason I want to say these things, and even this mess that's like hard to understand, is I kind of want to expose you to things that I don't have time to prove. But because you know the words, you now know what is important to go look up and read about, right? And what fits together with what. Okay. So the first one, so I'm going to do this, and then I'm actually going to kind of draw almost an example after that. Okay. So let R be Q mod F1 to FC, and I think I better assume that Q is regular local, so I don't mess up. Okay. So this is really a complete intersection ring. So something you get from it is called complexity. I'm not going to define fully, but what you do get is you get, if you look at the resolution, it's totally explicit. So the resolution F is the Q resolution, and you have a regular local ring, so it's finite. Okay? So this is just a finite amount of stuff that keeps getting put in. And this is the divided powers, which is the same size as a polynomial ring. So it's over Q. So you know about how big there are. You know how many monomials there are in every degree. So you know how big this is. And it's not that big. So in fact, you get a polynomial bound from this on the Betti numbers, which are the ranks of Fi in a minimal. Well, okay, erase that. I'm going to write it out explicitly. Is if F is a resolution of M over R, that's a minimal resolution. Okay, and I want to know the I Betti number. The definition of that is the rank of Fi as a free R module. Okay, but we built the resolution here. It might be too big, it might not be minimal. The minimal resolution is a direct summand of any resolution. So this is less than or equal to the rank of the GIs. But if you just count how many monomials there are of different degrees and times the ranks of the FIs, this can't grow very fast. So in fact, that is less than or equal to a constant times n. Am I using n? Oh, I raised to the c minus 1, where c was the number of equations F1, F up to Fc. Okay, questions? So these ranks only grow as fast as a polynomial at worst. And they might grow slower, and that's not true for other rings. So, other things are often wild. They grow exponentially. Okay, and then you also, from this, you get matrix factorizations. And for that, I would recommend reading Eisenberg. Actually, or Yoshino. Yoshino's book. Or Yoshino's book has a very nice chapter on those. And last thing I'll say, you get support varieties, which were very important. Okay, so you see this D here. This is the dual of S, so it has an S module structure. Okay, so we get an action of the poly ring S so I'm going to take the poly, I'm going to go down to R coefficients, so R T1 to Tn. It's not a great action. Oh, so that's actually sort of wrong. Okay, so you get an action on the homology of anything that G, so G tensor N, or homology of hom G into N, or any R module N. Okay. The T's act, you can multiply the T's on D as an S module structure, but there are let me just leave it like this, okay? So you get an action on the homology, but this is the tors of M and N. This is the homology is the set of all the tors, a direct sum of all the tors, and this is the direct sum of all the X of M and N. And what did I want to say? So in particular, so then if you take the case, so taking the case n equals k, you get x n k, which is, I should be more explicit. It's the direct sum of x I and k for all I. So this is a module over S over the polynomial ring. So this is a module, an S module. But this is nice because S is a very beautiful ring. It's just a polynomial ring. But what makes the whole thing really, really nice is Gulicksen's. It's called Gulicksen's finiteness theorem. That it is a finitely generated module. It is finitely generated. S module, and because of that, everything you learn in classical commutative algebra works for it. So in particular, the annihilator of this module tells you a lot about the dimension of the module. That's not true for an infinite module. But it's true for a finitely generated module. So in fact, the definition from Avramov of a support variety is that the support variety G star of M is the V, as in algebraic geometry V, of the vanishing set of the annihilator in the polynomial ring of this X and K over R. And this is an interesting variety. So it's a very interesting. So it's not irreducible. So I shouldn't call variety, but we do. So this variety tells you lots about the homological behavior of M, by which I don't just mean the resolution of M. So the dimension of this tells you how fast the resolution grows, like what degree polynomial. But the codimension, to what degree polynomial. But it also tells you, like, if you have two modules, how they interact, like how their x centaurs interact with each other. By knowing the support variety of each of them separately, and then looking at geometry of those two things and intersecting, tells you stuff about the interaction. So it tells you a lot of stuff. And this was only constructed for complete intersections in maybe 89. Yes, 89. And for years, people tried to find a similar support theory over other rings. And I know that non-commutative people worked with Hochschild cohomology for a while and annihilators of that. They only went so far, and then Josh in his thesis found a new version of support varieties that works for any that you can find for over any ring, and it has a homological significance. And it uses, instead of having a complete intersection, you just take the generators of the ideal defining the ring, and you make a Kazoo complex, and you work over that instead of working over the ring, and it just makes everything work like beautifully. So there's also a theory of this for not complete intersection. I think maybe that's good for today. Any questions? Yeah. It's a long day, I know, I'm sorry. This is really technical. Any questions?
More questions?
No. Okay.
Oh yeah. Is the 4MK finally generated?
That's a good question. I should know. Yeah. I don't know. Huh? Oh, it's Artinian. Yes, it's Artinian. Yes.
Right behind you.
It's a dual. It says Artinian. No, it's not a dual, but it's yeah. Right.
Also, right behind you. Wasn't G the resolution?
G was not minimal.
Oh, okay.
So take a minimal one, and the Betty number is the minimal one, right? And it's less than the one that we found because it's not minimal.
G's definition just had an F in it, so it was a little.
Oh, I'm sorry. This should have been some other letter here. Okay, yeah. Oh. Yeah, sorry. Okay.
Any other questions? Right, now let's thank God again. Tomorrow and okay.